Okay, yeah, let's start because it's 45 minutes or more, the presentation, and then the Q&A to be on time. Yeah, hello everyone. Thank you so much for your interest today to know more about internet computer and internet computer integrations. This seminar will be taught by Dieter Sommer. Dieter is the Senior Technical Program Manager at Definity Foundation. He has working tirelessly in the integrations in Ethereum and other integrations recently. And yeah, the first one, the topics today, the first one will be the internet computer integrates with other blockchains. And the second one, how internet computer connect blockchains to the real world. The duration of this seminar will be 1 hour, 45 minutes. Dieter will do a presentation, and then the other 15 minutes will be a Q&A. And yeah, let's start. Over to you, Dieter. Thank you so much for sure, everyone, and thank you for your time, Dieter.
Thank you very much for the introduction. Thanks everybody for having me here. It's very much a pleasure to give this seminar, The Internet Computer Integrating with Web 2 and Web 3. So let's get started. So the outline is that I'll give a brief introduction and then actually in reverse order, I will start with the warm-up session of the oracleless integration with Web 2 and then talk about the Web 3 with Web 3 integration. And there I'll first talk about different approaches to integrating and then ICP Bitcoin and ICP Ethereum integration to sketch it briefly and then conclude and we can have the discussion of 10 to 15 minutes in the end. So let's start with the introduction. So first of all, why Web 3 at all? I think that's the reason why we are here, because we all are Web 3 enthusiasts and we like it because there are multiple problems with Web 2. For example, the Web 2 is centralized. Network effects have led to an excessive concentration of power. For example, most of the services are controlled by single parties and it's all very centralized and users rely on those service providers and cannot themselves contribute how services evolve. So it's all very much an environment where users can't contribute themselves and everything is driven from centralized entities. And for example, public cloud runs everything on Web 2, but itself is run only by a handful of large public cloud providers. And now Web 3 tries to provide solutions, having a decentralized web, removing those single points of failure, single points of trust, so that we don't need to trust a single party anymore, yet have security. And now the idea is also that users, when being part of DAOs in Web 3, they can co-decide on how their services should evolve, for example. And that's one of the important things of Web 3. Don't trust single parties and also involve the users more, for example, with DAOs on how to, on evolvement of services that they use every day. So I think we all think, because we're here, that Web 3 is the future of the web. Now, Web 3 needs to be built in a way that it is as independent as possible of Web 2, which means also including public cloud. So don't build your blockchain nodes on public cloud, don't rely on public cloud when you build your decentralized Web 3 services, because otherwise they are not decentralized. And now, why connect different ecosystems? Why do those integrations? The actual topic of today's talk. Now there's these two parts of integrations, Web 3 with Web 2. I think that's very clear because much of the world's data, or most of the world's data these days, is still in Web 2, in the Web 2 ecosystem or in Web 2 silos. And we need to get this data over to Web 3 in order to make blockchain singularity happen, like meaning that all of the computations in the future will run on blockchain. That will be the ultimate goal here, but at least lots of the computations are running on blockchain. For this, we need to tap into the data sources of Web 2 to make this happen. So that's clear, we need this integration in a trustless way, ideally. And then Web 3 to Web 3, so integrating blockchains with each other. I think that's also very visible that Web 3 is increasingly embracing a cross-chain world, meaning that we have the cross-chain paradigm that dApps span multiple blockchains. So a dApp can now leverage multiple chains to provide its service in order, for example, to be most cost-effective or to at all be able to provide its service. Because, for example, Ethereum doesn't have enough storage, it can leverage storage on another blockchain and combine those aspects of the different chains. So that's something what cross-chain is. One important aspect, for example, moving tokens like ERC20 tokens or NFTs across blockchains, very important. or for example, allow smart contracts on one chain, like the IC, call smart contracts on another chain, like for example, Ethereum, or bring Bitcoin over to the internet computer. So all those things are use cases. And of course, don't just apply to the internet computer, but to any blockchain in the world. And yeah, ideally what we would have is arbitrary interactions between smart contracts on different chains. And here the important thing for both kinds of integrations is that the fewer new external components and new assumptions we need, the better. That's what trustlessness is and decentralization. So now looking at the internet computer as the case study today, it has already integrated with the Web2 world, thanks to the HTTP outcall feature, which means it can call to web API on the traditional web. And it already has integrated with the Bitcoin network in a trustless way. And what's upcoming is an Ethereum network integration. And now, what the goal for all of our integrations is Web2 as well as other Web3 ecosystems is to have them be trustless and fully on-chain. So not requiring new trust assumptions next to the trust assumptions for the ecosystems to be integrated, and not requiring new intermediaries, new parties to be introduced into the mix. And that's the approach we take for all of the integrations on the internet computer. And how to achieve that is through, on the one hand, integrating at the protocol level, and on the other hand, using what we call chain key signatures. So chain key cryptography, that's a form of advanced cryptography that uses concepts like secret sharing and multi-party computation to reduce trust assumptions to exactly realize this trustless approach. More about this later. So now let's go into the warm-up session on the Web2 with Web2 oracleless integration. Let's look at, from the view of the internet computer community, the past was that oracles are required for any form of Web3 to Web2 interaction. So how this works in the oracle world is that, for example, Ethereum, if you want to integrate with Web2, like you want to get an exchange rate from Coinbase into a smart contract, you would need an oracle off-chain, which is a trusted entity, and you would need an oracle smart contract as a proxy point on-chain, and now your smart contract would contact the oracle via a request to the oracle smart contract. The oracle would poll this oracle smart contract, fetch requests, execute them off-chain, put the results back into the oracle smart contract, and then the results would come back to your smart contract and the circle would be closed. That's it costs more than other approaches because you need to pay the oracle for its trust it provides, and also you need to pay the oracle, which means it's not a trustless solution. So those are both properties that we don't want to have. For this reason, the internet computer has thought, what could the future be? And the idea was having a direct communication from Web3 to Web2. So how this works is, at a conceptual level, that a canister can simply make a call to an HTTP server. So typically APIs are what are of interest here. For example, you can call an exchange rate API, fetch an exchange rate, and use it in your smart contract, like DeFi, for example. How this works technically is actually not too complicated. So you know that the internet computer is based on subnet blockchains. Each subnet is its own blockchain, and subnets communicate with each other using asynchronous message passing. And now this canister sits on one specific subnet, and when the canister requests now to make a call to an external HTTP server, what happens is that the canister makes this call to a system API on the subnet, and then the subnet nodes, all of them receive this call, and they all execute the call with the external HTTP server. And then the server responds back, and every node in the subnet receives this response. Now the problem might be that these responses have, for example, headers that contain sequence IDs or random IDs or timestamps at a very low granularity, like seconds or milliseconds. And in this case, the responses will not be exactly the same. And for this reason, we need to normalize them through the invocation of what we call a transformation function. Once normalized, the idea is that they are the same, like for example, just the exchange rate that you wanted to fetch, because that's the same, and all the variable parts of the responses are cut out. And then this response can go through consensus and can reach, can ensure that every node has the same input for its replicated computation. That's exactly the idea behind it. So every node makes the call, and then you normalize the response, and then the normalized responses are equal and can make it through consensus, and we can ensure that we still have determinism. That's the main problem to solve here. And we call this feature HTTPS outcalls because essentially a canister can outcall to an external service to the Web2 world, which is a novel paradigm in the blockchain world. This is pretty cool. I will show you a use case for this, but first let's talk about the limitations. So as I mentioned, it's applicable in all the situations where the responses are equal of the server or can be made equal. So if you make the same response from each replica, they are immediately equal, or you transform them to something equal, and then it works. And what's sometimes problematic is writing to Web2 this way, because every replica of the subnet would make the same post request, and for this to work, we need the API to be idempotent. For example, this can be reached by attaching an idempotency key. This is depending on the service whether this is supported or not. If it's supported, it means that we can make a write without problems to the Web2 scenario. If not, there are some further workarounds which we won't detail today, but it's possible. And if everything goes wrong, we can still use oracles on the internet computer also, of course, to do certain use cases. But the majority of use cases we think can be covered with this approach here, which means we don't need oracles for the majority of use cases like accessing API data outside. Now, one use case that has been already implemented is the so-called exchange rate canister seen here in the middle. This exchange rate canister can be queried by any client canister, for example, the dApp here on the left side. This client canister can then get an exchange rate for any currency or cryptocurrency that is out there. And how this works is that the exchange rate canister has a relatively large set of crypto exchanges and exchange rate sources like external central banks and other institutions from all over the world, Europe, Asia, US. And then it calls those or a subset of those, and then with an algorithm determines the actual price. So for example, if one of the providers provides a completely wrong result, this will be considered an outlier and won't affect the response. And all of this is possible completely without an oracle, so the canister can call out directly to all those services. So it is oracleless and it is trustless. No extra trust assumptions are required. This is a novelty in the blockchain world that this is possible. Otherwise, on other chains, you would need oracles to accomplish this, and you will need some trust in external parties. This is completely trustless, and everything is on-chain. So everything is on-chain, except for the outside services, of course, that we call here. So this is one interesting use case. This is already live, and you can use it. I put together some pointers to resources here, like the source code of the implementation, then the exchange rate canister source code. Unfortunately, the dashboard for HTTP outcalls we had that was tracking the frequency of use and stuff was deleted during an upgrade. So this is upcoming. There will be coming one out at some point. It's not available now. And there are also some Oracle projects driven by the community that are there in order to help if those outcalls would not be able to address a given use case. So this was already an overview of the integration of the internet computer with Web2 using an oracle-less approach. Next, I would like to go into the main topic of today, which is an integration of the internet computer of Web3 with another Web3 ecosystem, or in general also how different blockchains can integrate with each other. This is now the first topic, different approaches for connecting blockchains with each other. So to say, a bit of an overview what's out there in technology and how they compare in terms of properties. So overall, if you want to integrate two chains, chain A and chain B, we need two directions of authenticated data flow. So these arrows here indicate one direction of authenticated data flow, like from chain A to chain B. Let's say chain A is Ethereum, chain B is the internet computer. This would mean that the internet computer can read things from Ethereum. And what this usually requires is some changes on chain B, potentially a new smart contracts. There are also protocol changes and potentially also some new parties to be introduced between the chains as relays, for example, parties doing some other job, like for example, parties realizing a bridge. So this depends on the method that we are using for the integration. This is now one integration. I will show then a couple of different paradigms of how this can be achieved. And it's important, this is just one direction. If you want the other direction as well, we will need to build something on the other chain, potentially a smart contract or also a protocol change, depending on how we do it. And the paradigms used for both directions can be different and in practice are different in many cases between for a given pair of blockchains. Let's now look at a two-dimensional let's look at 2 dimensions of comparing the decentralization property of these integration approaches. The horizontal dimension is trust. So left is we need to trust, we have new trust assumptions to be made. Right is trustless, no new trust assumptions. So the right side here is preferable. And the vertical dimension is whether we need off-chain components to realize this integration. The further at the bottom, the point will be, or the approach will be, the more important off-chain components we have, the further at the top we are, the less important or the fewer off-chain components we have. And now, of course, the bottom left is what we don't want. It's the centralized approach, and the top right is the most decentralized approach. Now let's run through a couple of approaches. I will then explain in more detail later. So, for example, centralized bridges are at the bottom left because they are trusted. You need to trust them to work properly in order to be secure, and major functionality components are off-chain. So both of those properties make it a not very desirable solution. So layer 0 is one example of those. Then the majority of bridges those days are off-chain validators or off-chain validated, externally validated bridges. There are a couple of different approaches there, resulting in a spectrum of trust and decentralization. For example, what you have here is trusted bridges, like the wormhole bridge, where the parties involved in the bridge are trusted to behave correctly, and they have something to lose, for example, reputation, because they have a big business behind themselves, behind their name. That's one approach to do it. Another approach is to have bonded bridges. So there is value at stake, and if the bridge parties don't behave properly, this value can get slashed. That's further right on the trust spectrum, but we can even go further with optimistic bridges, where even if all the bridges' private keys get compromised, if there's a single party that can complain that the bridges, that there was misbehavior, it's still secure. That's why it's further right, but it's also more on the bottom because it has a very, very important off-chain component that's crucial for security and not just availability. Could be even further down potentially. So this is probably, this category of those 3 is probably the majority of bridges we have out there today. And now comes the most interesting ones, more on the right. So on the one hand, light client solutions, of which I will mention 2. So normal light client solutions, having an on-chain light client. They are trustless in the light client model, which is very good. That's why they're much on the right side. However, they rely on additional components being off-chain, like relay nodes, which means we have availability assumptions that rely on off-chain components, which is not so nice. And also one problem is that they are not feasible to implement it for many pairs of blockchains. So you can't build them for example, Ethereum and Cosmos easily to integrate in both ways. This problem gets solved by something which is called on-chain zero-knowledge light clients and off-chain zero-knowledge prover networks working in tandem. Example, CK Bridge, which is in beta. This is pretty interesting. This is trustless in the light client model as well. However, it's further down because it requires a huge off-chain network of machines computing those zero-knowledge proofs that make an on-chain validation possible. And now we can do better than that even, so we can do a direct integration, having an on-chain client and a native integration. I will put this at the top right because this is completely trustless, not just in the light client model, and as well, it has no off-chain components. And that's the approach that the internet computer uses for Bitcoin integration and Ethereum integration. And now I'd like to run you through the major paradigms of integration here, starting with the centralized bridges, and give an overview of them in a bit more detail. So in a centralized bridge, to connect chain A with chain B, we need an off-chain trusted party. This is one or maybe a small number of off-chain parties. Like for example, this layer 0 protocol requires 2 off-chain parties, and the assumption is that they don't collude with each other. I put them into the centralized bridge because this is very, very centralized. And then you have a bridge smart contract on chain B, and then this off-chain party just provides consensus artifacts from chain A to the smart contract, and the smart contract believes that this is correct without cryptographic verification. This is the important part. So we just have trust in this off-chain body in the middle here that it behaves correctly and doesn't lie to the smart contract in chain B. And if this is the case, the integration works. And this bridge smart contract then assumes that this claim of this off-chain body is correct. And that's why this off-chain body must be trusted. This makes the whole approach weak. And we can use it in almost all, we can use it for any kind of blockchain integration in both directions because it doesn't have any complex crypto protocols. So advantages are this is extremely simple because it doesn't have advanced crypto. It's very efficient also because it doesn't have advanced crypto. The problem is it's not trustless. It requires full trust in one or in few parties sitting between the two blockchains here. And that's why it's the weakest trust model. So it's not the best bridging model. Let's now move further to the right and up to better decentralization. So I'll now capture all of those in one shot. Again, with the two blockchains, we want to have communication in an authenticated way from A to B. Now, how we do that here is that we have an off-chain validator network. So this is a network of parties which collectively are called a bridge. This can be, for example, the wormhole bridge, like 19 parties, and 11 of them must agree in order for something to happen. And now the idea is these off-chain parties, each of them validate consensus artifacts or things happening on chain A. And if a majority of them or supermajority, a defined number of them agree that something happened, they would issue a multi-signature or threshold signature and send this event to the bridge smart contract on chain B. And then the bridge smart contract would again believe that this statement is correct because it has been made by a majority of people. So we have had consensus externally among this off-chain validator network in order for it to be more secure. So that's definitely much, much better than this single external party because it's a larger set of external parties. Maybe it's a set of parties you trust a lot in each of them. So if then a majority of them, like 11 out of 19 say something is correct, then this is already much stronger than if a single party says so. But it's still not trustless. You need to trust this collective of parties to together not screw over the user, so to say. And this approach can also be easily implemented in both directions for essentially any blockchain that supports smart contracts because it relies on these external parties and doesn't have strong requirements on what the smart contracts on-chain can do. And this approach still is rather simple and it's efficient also. Drawback is that we still have major additional trust assumptions besides the two blockchains themselves. So it's not trustless, and this is the main problem of this approach. Now let's move to the trustless approaches on the right. Let's first look at the light client solution, like the on-chain light client. So again, the two chains that need to be integrated, we now have relayers between them. That's a set of parties that don't need to be trusted for anything. They only need to be available to do their job of relaying artifacts from A to B, namely consensus artifacts like block headers and everything you need to validate consensus on this smart contract on chain B in a light client fashion. So the idea is that this smart contract can cryptographically validate correct state transitions on chain A using a light client. And this is secure in the light client model. So it's trustless in this model, which is very good because the relayers cannot make something wrong being accepted. They just can lead to a denial of service if they don't relay artifacts. So that's already very strong in the trust approach, but it still requires off-chain components. And what's here the main challenge is that such a light client is not easily implementable on many blockchains. So the problem here is signature. This validation of consensus requires that signatures from chain A be validated, and now it helps if the chain B smart contracts can access what's called pre-compiles, like can have native implementation of signature verification, for example, for ECDSA or for BLS or whatever chain A uses in its consensus. And if that's available, it's easier to build those light clients, but still it might be not gas efficient or not even possible to execute those computations within a block time, or in Ethereum, it might get prohibitively expensive, like consuming half a block costs you thousands of dollars per thing. It would consume a majority of the, or a large amount of the overall Ethereum compute capacity. So the problem is it's not easily implementable on many chains. Otherwise, it's a nice solution, except for also the relayers. And yeah, both directions rarely work with this model in most chains. So it's trustless in the light client model, very nice. But it uses relayers as off-chain components, not so nice, but yeah, tolerable for many, but still we don't want it really. And one big challenge, it's often not feasible to implement this model because the light client can't be built on many chains because of efficiency reasons. This is exactly what these on-chain zero-knowledge light clients try to resolve. Let's look now how this works. Again, the two chains. For this, the work, we put up a so-called zero-knowledge proof generation and relay network. This can be a larger number of machines. Those fetch, again, consensus artifacts from chain A, validate them, and if they deem them valid, they generate a zero-knowledge proof, so a C-case NARC. And an even compressed version uses a recursive zero-knowledge proof technique of this to make it very, very small and efficiently verifiable. And then this efficiently verifiable proof of consensus of chain A having happened correctly is sent to this light client on chain B, and then it can verify it efficiently. So for example, on Ethereum can verify with less than 230,000 gas units a consensus, a state transition of the Cosmos network, which requires 128 signatures to be verified. This is extremely efficient. So this is actually an interesting technology. This already said. So it's trustless in the light client model, like the approach before, and it solves the problem of feasibility and gas efficiency. So you can implement such light clients on, I would say, any smart contract chain that's somewhat reasonable. There's also drawbacks to this, because otherwise it would be perfect. Drawbacks are that this zero-knowledge proof generation is not a small thing. This is massive. So, for example, from the currently most efficient protocol to make a proof for a Cosmos consensus, for a Cosmos state transition, and want to verify this on Ethereum. So generating this proof requires 128 high-powered machines, like 96 core machines, that are together generating this proof. This is a huge off-chain infrastructure that's running a huge investment, and the problem is that this reduces the availability property, because this is a huge thing that's running off-chain that's required to connect those two chains. And running this off-chain means, yeah, we have now a huge component probably running in the public cloud, which is required for the cross-chain communication to work. So that's not nice, because there's this large off-chain component. So this is again against decentralization. The nice thing is it's also possible to, so I said this already, that you can implement this approach usually for bidirectional communication for most chains, or for any smart contract chain. So I now gave you an overview of almost all the approaches. Now the final one on the top right, which is the most desirable state to be, is the on-chain client and native integration approach, which is trustless and has no off-chain components. And again, the two chains, the idea to have data in an authenticated way flow from chain A to chain B is achieved in a way that we implement a client for chain A on chain B. This can be as part of smart contract, or this could be as part of the protocol as a combination thereof. It doesn't matter, it must look and feel and have security properties of a blockchain client for chain A. And once we have that, we have the authentic communication in this direction to chain B. And the authenticated communication to chain A from chain B can be achieved using what's called threshold ECDSA. So threshold ECDSA allows chain B in a trustless way to create digital signatures for transactions of chain A to be signed. And this requires now authenticated communication from chain B to chain A without any light client or anything on chain A, which is nice. So you just need to do stuff on chain B and can integrate chain A. So there's a couple of advantages to this. So it's completely trustless, not just in the light client model, but in the model of chain A and chain B. So this is very nice. Everything can be fully on chain. As you see, there are no additional servers in the middle between the two chains, no relays, nothing else, which is very nice. So those two things lead to this being the most decentralized model, so being at the top right of the graph I showed before. It's also the most powerful form of integration because it's direct. It means that smart contracts of B can directly interact with smart contracts on A without stuff on A being implemented or happening, which is very, very powerful. And also it works if chain A does not support smart contracts. That's exactly where Bitcoin comes in. Bitcoin integration doesn't work with any of the other approaches except that are trustless. So it does work with trusted bridges. But this is This approach is the only trustless approach to work for integrating with Bitcoin because Bitcoin doesn't have smart contracts. And yeah, that's what makes it very powerful. There are also drawbacks because it's complex to build, it's time intensive to build because you need to change the protocol, you need to build threshold ECDSA, EDDSA protocols. This is not easy stuff, so this is hard crypto that you need to solve. And also the computational effort of computing threshold ECDSA signatures is not small, but it's much less effort than building these proofs, these zero knowledge SNART proofs that I showed in the previous approach of the CK-led clients. So from this perspective, it has lots of advantages and some disadvantages, but they are not too bad. So this is a very nice approach, and that's why we use this also for the internet computer. Yeah, now you have learned a spectrum, two-dimensional spectrum of integration approaches from very centralized to very decentralized, and the rest of the talk I will talk about decentralized approaches taken on the internet computer. So this top right approach here that has been taken for Bitcoin and Ethereum on the internet computer. So let's next dive into this, ICP and Bitcoin native integration. So you know this picture already, chain A is now Bitcoin, chain B is the internet computer. And as I said, on the internet computer, we need a client for Bitcoin to be implemented and we need threshold ECDSA. Those are the two components. If we have those, we have a trustless integration without intermediaries. For this, we need one basic building block. This building block is threshold ECDSA. Threshold ECDSA is a building block that allows us to have a private key, like an ECDSA signing key, secret shared across all the replicas of an internet computer subnet. Say we have a subnet of 34 nodes. Then when generating this key, it's getting generated in a secret shared way. So every node gets a share, and one share has 0 bits of information of the key. It's not chunking up the key, but it's doing it in a smarter way that you need at least 1/3 plus 1 of all the shares, random. So any 1/3 plus 1 of the shares in order to make a signature with the key or to reconstruct it. The key itself is never existing in reconstructed form. It's generated already in secret shared form. And when the subnet makes signatures, it's also not reconstructed, but the signing is done with multi-party computation. So now we could have any canister on any application subnet of the internet computer. It can now ask for its own public key. Every canister gets its own private public key pair virtually, which is derived from one master private key, which is the one secret shared on the top left on this subnet. And with this public key, it can then, for example, derive a Bitcoin or Ethereum address. And that's exactly how this integration works. So the canister now can act like a user on a Bitcoin or Ethereum network, for example, or other blockchains that support ECDSA. And then the canister can also request a signature with their private key. They never see their private key, but they can say, hey, I want the signature with my private key. And then this threshold ECDSA subnet would compute the signature in a completely decentralized way. So it means that at least 1/3 plus 1 of the parties of the secret key of the key shares are required to compute this signature. If fewer parties participate, it wouldn't work. So it means that we can tolerate a certain threshold of dishonest parties on this ECDSA signing subnet, and the system is still completely secure. And in some way, conceptually, what we get here is a functionality like an on-chain hardware security module, but just realized with clever software. And there's a couple of mechanisms in here which help increase the security of this. So on the one hand, we have 34 nodes holding key shares, which is a larger number. So 11 of them can be faulty and it's still secure, which is pretty good number, I think. Next, we have a periodic resharing of the key, which means every time period of, I don't know what exactly, but every certain time period, the key is shared in a fresh way. So if an attacker has obtained some key shares, they are worthless after this resharing, which is a very nice thing. And also what's enabled soon in the months to come will be a trusted execution environment support for this subnet or for other subnets as well, which means that all the memory will be encrypted, for example. So this makes it nice because it makes it much harder to attack these nodes and to extract public key shares. So all of those things make the system very secure and completely trustless. So much more trustless than any outside of the blockchain parties you need to trust. And for further resilience, we have a mechanism on the internet computer to back up these private keys to other subnets. So this backup means that a new resharing of this private key can be stored or can be generated on another subnet. And so if one subnet should be completely destroyed for some reason, like a software bug or whatever, the key is still available. That's important because the key might secure large amounts of value in scenarios like Bitcoin integration or Ethereum integration. So much to threshold ECDSA. Let's now go into Bitcoin. I don't know how many know how the Bitcoin protocol works conceptually. Let me briefly recap it. So if Alice holds some Bitcoin, which is unspent transaction outputs in the Bitcoin network, you can think of those as coins. She can decide to spend them and send them, for example, to Bob, the one with the green public key. And now, let's say Alice wants to make such a transaction to Bob. Then she can assemble a transaction and she inputs into transaction so-called unspent transaction outputs or unspent coins from previous transactions where other people have sent coins to her, which means to her blue public key. Now she can include those unspent outputs into a new transaction as inputs, can define that the output should go to the green public key of Bob here, and then she can sign with a blue private key those transactions to authenticate that she is indeed the owner of those outputs. And once those is done, the transaction is complete and can be submitted to the Bitcoin network, which means it goes into a block if it's mined and has enough fees. Then the Bitcoin block goes into the Bitcoin blockchain, hopefully, is included, and then further blocks grow on top of it. And at some point, like after 6 confirmations, for example, you might accept it as final enough, so it's probabilistic finality. And then the transaction is valid and Bob could spend it to somebody else. So now if you look at how the internet computer integrates with Bitcoin in a bit more detail, I just gave a rough overview before. The goals are to have web speed smart contracts and a direct integration, so no additional trust assumptions being required and no additional parties being required. And there should be an easy-to-use developer experience with easy-to-use APIs and a great end-user experience. Achieving all of this is not easy, so the challenges are essentially that canisters need to be able to directly receive and hold Bitcoin on the Bitcoin blockchain. So a user can send Bitcoin to a canister smart contract, and then the canister can send Bitcoin to other canister smart contracts or to users, like to any other Bitcoin address. Those are the 2 challenges to address. And I'll show you now in a bit more detail, but still at a high level, how that works. On the left, internet computer, in the middle, the Bitcoin network. So we want the direct trustless integration, as I already said. Means no intermediaries like relays and other stuff in between, particularly no trusted parties. And now let's look at the challenges we have to resolve. So first of all, we said canisters should be able to receive and hold Bitcoin, which means canisters need an ECDSA public key. And how this works is that we implemented this threshold ECDSA mechanism I showed before as a system component of the internet computer. And now canisters can ask this component for their public key. They can have multiple public keys, but let's keep it simple. Let's talk about one. So they can ask, what's my public key? And then the canister can get their public key, can derive a Bitcoin address from this. This is straightforward computation in a smart contract. And then send this Bitcoin address to people to transfer money to them. For example, the canister could be an exchange, a decentralized exchange, and this address could be the deposit address for a specific customer. Then the customer could send Bitcoin to this deposit address on the Bitcoin network. That wouldn't require anything else to work. So then the canister would hold the Bitcoin, but it couldn't do anything with it yet. In order for it to be able to do anything, the canister needs to, so we need more. So the canister needs essentially to be able to transfer Bitcoin to other canisters and users. And for this, it first of all needs to be able to see their UTXOs. So these transaction outputs I showed earlier that need to be used for putting a transaction together. How this works is we need a client for Bitcoin on the internet computer. We implemented this as part of the protocol and smart contracts as a mix. I just show it as this blue box here. And this essentially works in a way that this is activated on one subnet, and all the replicas, all the machines on this subnet connect to the Bitcoin network like a Bitcoin node and pull in every new Bitcoin block. And then process this Bitcoin block and extract all the spent and unspent transaction outputs. And then this Bitcoin component keeps the complete Bitcoin state in memory, means all the UTXOs, not all the block history, that's not required, but all the UTXOs. This consumes 40 gigabyte of memory in the smart contract, which is pretty much, you can't do it on many blockchains. I think the internet computer is the only one where you can currently do this. And this smart contract can now be queried by, for example, this canister up there. and it can ask what's my Bitcoin UTXOs for my Bitcoin address. And then it gets back the set of UTXOs it holds, and then it can also make transactions with those. So it can assemble a transaction, for example, putting 2 of those 3 UTXOs, these unspent coins, as transaction inputs into the transaction, define to whom the output should go, like for example to Bob, and then it can sign the transaction. This is now the technically most hard part. It's this threshold ECDSA signing protocol. So this is, as I mentioned already, realized by this system component that realizes this threshold ECDSA scheme. So trustless signing without needing to trust anything, without a key that's anywhere, it's shared among many parties. So this is the most secure way to compute digital signatures in a decentralized way. And now the canister can ask this system component for ECDSA signatures and attach those to the transaction, and then send the transaction to the Bitcoin network again by calling a functionality in this Bitcoin integration component, and then all the connected nodes would send this transaction, would flood this transaction into the Bitcoin network. And then the transaction would be mined, hopefully, if there's enough fees specified, and would at some point be a valid transaction in the Bitcoin network if there's blocks grown above this block. So that's roughly how it works. Completely trustless, no trust assumptions in addition to those of the Bitcoin network and the IC, and also no additional parties required. And now what does this bring us? It brings Bitcoin liquidity to the internet computer. It has a great end user experience because users can use the WebAuthn protocol of internet identity to authenticate to smart contracts and use Bitcoin. For example, OpenChat has integrated Bitcoin transfers using an on-chain variant of Bitcoin called CKBTC, which can be transferred with low fees and high throughput on the internet computer. More about this a bit later. We can do things like decentralized ICP BTC exchanges, lending, borrowing using Bitcoin, decentralized fundraising using Bitcoin, buying NFTs with Bitcoin, and so on. So we set the technical foundation now with this integration for many, many use cases to happen. And if you look now at the big picture of how this looks from an architecture perspective, so you see one subnet with the Bitcoin logo here runs this Bitcoin full node, essentially, or close to a full node on chain, exposes an API to any canister on the top left. And now the canister can query these UTXOs and use threshold ECDSA to sign transaction. And with this architecture, we can have this completely trustless integration between the two networks and having Bitcoin on the IC, because smart contracts can arbitrarily control Bitcoin on the Bitcoin network. A very, very, very powerful model to integrate two blockchains with each other. But that's not all. I mentioned already there's an on-chain version of Bitcoin. It's called Chain Key Bitcoin, or CKBTC. Chain Key means it's realized with this chain key technology. So here particularly this threshold ECDSA technology. That's why this name. It's much, much better than a regular wrapped token, because a wrapped token oftentimes uses strong trust assumptions. This does not. It's completely trustless because it relies on this native Bitcoin integration. And now any decentralized app on the top left here can use this CKBTC ledger to transfer CKBTC tokens on the internet computer, and each CKBTC token is backed by a real Bitcoin on the Bitcoin network. And this one is, this backing Bitcoin are held by the CKBTC minter, which is a smart contract. So there's always a guarantee of one-to-one backing of those on-chain tokens. And now what's unique in the world is that this implementation uses, so it uses, in addition to the native Bitcoin integration, also a feature of this HTTPS outcalls, this Web2 integration, in order to realize a decentralized on-chain know your transaction system. So KYT, know your transaction, is an approach to query external parties who have analyzed blockchain transactions and have flagged illegal transactions, for example, transactions related to terrorist activities, transactions related to frauds and other things. So for example, if big hacks of bridges happen, which sometimes happens, and those tokens can be traced on the blockchain, and then Chainalysis, one of those analysis companies, they would flag those stolen tokens as illegitimate, and we would now prevent those illegitimate tokens to enter the CKBTC minter. This is important because regulations in the blockchain industry, particularly in some countries, are now picking up more and more. And for example, US and Europe will have much stronger regulations to not allow anything in the blockchain space. And this is already now a couple of steps ahead the rest of the world by doing this on-chain know your transaction screening and preventing those illegal or illegitimate tokens to enter the IC ecosystem. So that's very nice. And in the future, we will further decentralize this in a way that more of those analytics companies will be added so that we then can take a quorum vote whether a given UTXO or a given coin coming from another ecosystem is related to illegal activity or not. And then with this decentralized approach, we have something that's very, very powerful in terms of being even future-proof with regulations that are likely to come up here in this space. Some resources here, the slides that you will receive later are about some dashboards like the Bitcoin CKBTC dashboard where you can see all the transactions. For CKBTC, also the source code here at the top of the implementation, and then the two most important research papers related to what I've shown now about the Bitcoin integration. So much to that. Now briefly about the native Ethereum integration. This is something that's taking a somewhat similar approach conceptually. I showed this picture I've shown for Bitcoin. It looks very similar, just instead of the Bitcoin node, you see here an Ethereum node that's looking like an on-chain Ethereum node. It's actually implemented differently, but it has an API like an on-chain Ethereum node. And then any canister shown on the top left can use this and threshold DCDSA again to arbitrarily interact with the Ethereum network. So read in a secure way from the Ethereum network and write in a secure way to the Ethereum network. Very, very powerful. How we achieve it is that in one subnet, Ethereum will be enabled and there will be an Ethereum pruned full node being run on each of the subnet nodes. And then we use this HTTP outcalls feature to locally host to the respective local Ethereum node in order to connect and in order to query it or send transactions to it. And this, then the response is going through internet computer consensus, and thus we can reach a security model that's very, very similar to a full Ethereum node running on-chain. And this is something that's pretty nice. It's a somewhat stronger security model than having an Ethereum light client on-chain because it doesn't have the weaker model of the light client model. So this is really more or less the strongest you can do in terms of trustless integration. That's already it about Ethereum. This is currently work in progress. It will allow a lot of new use cases and also bringing, for example, ERC20 tokens, NFTs, and so on over to the internet computer. This is already the time to conclude. So what I've been talking about now is really an approach, a large initiative of combining the powers of blockchain and Web2. Not just the power of one blockchain, but powers of multiple blockchains. So on the one hand, we have integration with Web2 in a trustless way. On the other hand, we have an integration with the largest asset store like Bitcoin and the internet computer, and we have an integration between the internet computer and the largest smart contract blockchain currently, Ethereum, once this is done. So this is both very powerful, and all taken together is a huge step forward for the internet computer. And why do we do it with this native trustless integration? Because it's the strongest security model, it's the best you can have. You don't introduce new assumptions, no new parties. And yeah, it's essentially as independent of Web2 as possible because we don't need to run any components in the public cloud. This is very, very powerful. So it's very powerful for the availability part of security because, you know, security usually comprises three aspects, which is CIA, confidentiality, integrity, and availability. Availability is often the one talked about least, and I think it's just worth mentioning with this everything on-chain approach that the internet computer takes. Availability is also considered as a first-class citizen, and it is a very important part of security. That's why we want this fully on-chain model, no off-chain components next to the systems we integrate. And now what we have is that IC smart contracts can directly interact with Bitcoin and soon also with the Ethereum network and smart contracts there. And what are the use cases of this? So I think there's many, like IC decentralized apps can now leverage the combined power of the internet computer and the natively integrated blockchains and Web2, like the big data source of Web2. And also Bitcoin received smart contracts, like canister smart contracts of the IC, because they can now hold Bitcoin natively. Very, very powerful. The IC also got fast and efficient on-chain Bitcoin, like the version like CKBTC, which is the on-chain variant of Bitcoin. Then Ethereum integration, this can help to bring further liquidity to IC smart contracts, like for example to taxes and so on. So this is also very powerful, like Ether, USDC, USDT, stablecoins, all of those things can be brought over using this chain key technology with the direct integration. And then, for example, Ethereum smart contracts can offload computational storage to the IC. This is something very nice. And there's lots of use cases overall we can realize with this approach, like taxes, decentralized borrowing protocols, NFT, buying NFTs with different cryptocurrencies, fundraising in Bitcoin or Ether, and so on. So there's no boundaries to what we can do here. And this is also what I want to close with, and I would like to open the floor for discussions now. So thank you very much for your attention, and now I'm open for questions. I hope we have some time. Yes, 8 minutes, 9 minutes.
Yeah, so Thomas, do you have any questions? Because Thomas is an expert in...
Hang on. Oh, can you guys? Oh, hang on. What happened to my video?
We can
hey,
hear
now,
you.
interesting presentation. I think the reason Lu Yao is asking is so we have an effort in the IETF to standardize the transfer protocol, but the strict condition is that either side or both sides could be private permission, completely closed networks. So the idea that you can see the smart contract in the other blockchain and vice versa doesn't apply. Cannot apply. So no one's going to let you see my smart contract. So this is one of the use cases that we're addressing in the IETF.
Okay, that's also interesting. So you're talking about two permission private blockchains that want to be integrated with each other, and you want to standardize this.
Well, so the integration, so the transfer protocol must be able to address. So it's basically just two networks, just unidirectional. That's hard enough, right? So there's no atomic swaps because you can't see each other's. You know, and you can't assume Alice and Bob are present on both networks, which is a lot of the assumptions of many of the hash lock schemes. So, but the key thing is one of both could be blockchain, one of both could be a monolithic system like mainframes, because apparently people are still using mainframes, and apparently there's a shortage of COBOL developers. If you guys are old enough to know what COBOL is.
Much of the world state is in those systems, unfortunately. Yes, that's a very important point. So, that sounds like an interesting challenge, actually. Could you also point me to this standardization group? This sounds extremely interesting.
Yes, I will post the link to the chat so that everyone can see. Give me 1 second. But this is, this is interesting stuff, and I think there's a to be perfectly honest, there's a lot you spoke about. This is like dense, right? So it'd be good to like break down all the stuff that you've discussed today and see if there's any way to, any opportunity to collaborate.
Yeah, definitely. Yeah. So I wonder what the trust model is that you want to achieve in your standard. Whether some trusted bridges.
Yeah. So people ask that question all the time. So we assume it's a protocol. It's just like SSL. It's just like TLS. It's like, what's the trust model for TLS? Well, it depends on the sender and the receiver. So it's a protocol definition. Who you trust to run it is out of scope. Like the IETF doesn't say anything. Just like TLS doesn't say, do you trust the sender? Do you trust the receiver? It's just a protocol specification. Right.
That would be really interesting to see the work there. Yeah, this would be very interesting for me also.
Yeah, let me post the link. But
it's
a very interesting presentation.
Cool. Any other questions or comments?
Oh, actually, Michael is here. Like, he want to present this Shiku and Yumi, so the application on the internet computer. So, and we also airdropped an NFT to Dieter. It should already be in your wallet. It's the Ethereum address, so it's kind of like this cross-chain implementation. So Michael, do you want to present a little bit? So.
Yeah, hi everyone. Actually, I just want to thank you, Dieter, for all these details, explanation on the CK-BTC. And what's important is that you're building this for dApps, right? And for dApps also from other chains to be able to come and bridge, well, trustlessly with the internet computer. And I just wanted to say here that, yeah, we as a Yumi Marketplace and Shiku Metaverse, we are exactly an example of dApps that are now exploring the CK-BTC and this native integration with Bitcoin and Ethereum, because we really see the potential for our dApps to widen the audience and the communities, to enable people to buy the NFTs and to interact in the metaverse directly with tokens and other cryptocurrencies directly from the other chains without having all these risks from the traditional bridges. So we really see a lot of use cases. People can start doing DeFi with CK-BTC on NFT marketplaces. We can start seeing people being able to buy directly the NFTs with CK-BTC. We can integrate this into the various aspects of our dApps. And I think, yeah, the use cases are really big, and it's time to explore now. And yeah, we're just an example of dApps that are discussing this now and seeing what are all the advantages and how we can attract more people to the internet computer thanks to this. Yeah.
I'm very happy to hear your interest in these technologies. Yeah, we are currently working with full force on the Ethereum integration, and yeah, lots of stuff is moving forward here, but it's a sizable project and will take some time.
Yeah, and especially if you think that, for example, on Yumi, like we launched the gold NFTs now. So imagine, right? People want to buy a gold NFT with the CK-BTC. We all know that Bitcoin is kind of like the digital gold, so it's kind of nice when you can imagine
buy
this.
Real gold with Bitcoin. Yeah, that's a pretty compelling use case. Very nice.
It's extremely interesting, right? But then also for the metaverse, being able to bring lots of users from Ethereum communities, thanks to the Ethereum integration, so that they can directly then purchase with different currencies, I think is very important for growing the ecosystem of the ICP as well. Yeah. So yeah, thanks.
I'm very happy to hear that you have such interesting use cases on your side. Yeah, that's very cool. Yeah.
That's all from our side. Yeah, thanks.
Good. Anything else? Anyone else? Questions? Comments?
I have a last question. So I think I very much like your y-axis thing on the decentralization and on-chain off-chain. I would, and also it's related to Thomas' question. I'm wondering if we are adding another z-axis on privacy, what's more you can add to those solutions, like the consideration of privacy.
Privacy, yeah, I mean, that's a good point. So currently, I mean, so for privacy, you have a different model on different blockchains. Like, for example, on Ethereum, everything is public on the blocks. On the internet computer, blocks by default are not public, but only relevant information of smart contracts is published. So there's stronger privacy on the internet computer. This is also amplified by integrating this trusted execution technology, which will be launched in the near term, which then makes it much harder for a hacker or for the node provider themselves, for example, to extract the RAM or disk content. So this will be made very hard because of this trusted execution technology. So that's why privacy is rather strong on the internet computer. Also, the ecosystem on the internet computer is currently working on what's called fully homomorphic encryption on a protocol that's implementable in a and reasonably efficient computationally, but that's something that's still a bit away, but there's currently work by one of our top cryptographers going on fully homomorphic encryption, which will be computations on encrypted values without learning the underlying values. So that's a thing very important for privacy, outside of the integration of blockchains, but yeah, just in general, because you mentioned privacy.
Oh, sounds very interesting. So I think this TE plus smart contract solution sounds very natural, because TE is providing privacy, and then smart contract is providing this automation and transparency. So but however, it also sounds like TE is another centralized party we need to trust.
No, TE is it's a secure computing element inside the machine, so inside the CPU. It's secure enclave inside the CPU, and it means all the RAM content is encrypted and the disk content using private keys stored in there. So it's an additional layer of defense inside each machine of the data center.
Oh, so
no additional assumptions.
It's not TE, it's something else.
So trusted execution environment, something like AMD, SCV, SNB in our case.
Secure enclaves is the
Secure enclaves, yeah. Thanks, Thomas.
It's the easy way to use.
Oh, the secure encase. Oh, that's very interesting. Can you share your slides with us?
Yeah, sure. I will send the PDF to you.
Okay, cool. Thank you so much. Okay, I learned something new. So secure enclaves is something do not need trust on another party.
No, it reduces, so it helps keep information private, essentially. Yeah, it's an additional layer of defense inside a machine, inside the data center to make things more private. It's a very nice thing. It's also not perfect, but it just raises the bar for an attack and makes it harder to compromise data.
Okay, thank you so much. Thank you so much. Learned a lot today.
Good, okay, thanks everybody.
Yes.
It was a pleasure for me to be here today. And have a good morning, have a good evening.
Thank you, Dieter. Let me.
Thank you, Dieter. Thanks. Bye-bye.
Bye-bye.
Sorry.
Goodbye, everybody.
Yeah. That's fine.